Second part of what we learned about on the 15th, today, Monday, was how the body handles protons and bicarbonates and how it relates to respiratory function and kidney function. And so this is outlined here, and this is basically what we drew up. We started with a blank sheet of paper and we filled in this equation here, and then we talked about how the respiratory system helps to handle carbon dioxide and breathe off carbon dioxide, which we talked about in our respiratory component. But we also have over here the new information that we're learning about here is the protons and how they're working to, or how they're handled by the renal system, and then how bicarbonate here is handled by the renal system as well. So what we're looking at then is trying to maintain this pH balance that's so important for the successful homeostasis. And then what we have are several different types of cells that are important for it. And so we basically began by drawing this out, reminding ourselves the name of the enzyme here, carbonic anhydrase. It's important for regulating this conversion of CO2 and water into carbonic acid. Knowing the names of these different things, like carbonic acid, speak what it is, and then how that in turn quickly dissociates into protons and bicarbonates. So we went through that, and then what we did is that we said, well, in the kidney, what we have are two different types of cells. One is the type A cells, and these type A cells are important for excretion of protons from the nephron into the nephron, rather, from the blood. And so the idea is you're excreting, you're getting rid of it. And this is an ATP-dependent process, an ATP-dependent pump that's responsible for that. And it's active during acidosis. And so I circled the A here to make a connection to the name of the cell, which is the type A cells. And so these are cells that are present in our distal convoluted tubule. And then the other thing that I pointed out, the next thing was talking about these type B cells. These are important for excretion of bicarbonate, active during alkalosis, when the cell is when the body and the blood has become basic. And so circling the B there to help correspond it to the B there, or you could look at bicarbonate and think of that as a B, whatever helps you sort that out. And then I went to the PowerPoint and wanted to point out a couple of things about this. The text is small here, but there are a couple of features that I wanted to illustrate and make sure were really clear. So I went ahead and did that. And so looking at the top one up here, what we have are type A cells that are present within this distal convoluted tubule. These become active during acidosis, if you remember what we talked about before. The main thing I wanted you guys to walk away with was that we have these proton pumps that are responsible for pushing the blood out they're on the apical side of the membrane, and they're responsible for pushing the protons out into the lumen of the nephron. And so this is ATP dependent, pumping it out. And what we have then is we have bicarbonate that in turn is released through and goes out through a secondary active mechanism along its concentration gradient here. So that's what we're seeing as it ends up leaving the cell and exiting as a buffer. So the other thing that we did is we talked about type B cells. In type B cells, what we have are bicarbonate that is permitted to flow out into the lumen of the collecting duct here, and it's an antiporter that we're using to help release the bicarbonate from the interior of the cell and out into the nephron, lumen of the nephron. And this is in part, we can see that we also have the proton pumps on the basolateral side of the cell here, and that these are bringing the protons, keeping them in the blood. And so this helps rectify the situation if the blood has become really bicarbonate, or it's really basic, and so we want more acid around to help counteract that, and our proton concentration is low. And then up here, obviously, this is when our proton levels are high, and we want to be able to help excrete it. So these are ways that we can actually be able to have our kidneys work to manage protons and bicarbonate. And so going back to our PDF here, what we can see is in two different examples here. We have respiratory acidosis and metabolic acidosis. And in respiratory acidosis, if we lose some functioning of our lungs, then we're going to have an elevation of our CO2 levels in our blood because we can't breathe it off like we normally would. And that in turn is going to cause an elevation of the number of protons we have, or a drop in our pH. Keep that straight, don't get those mixed up. And our kidney will compensate for this excess of protons here. And so this is when our A cells would be really active, trying to clear out the protons that we have. In metabolic acidosis, this is a case in which you have something would have occurred, and I'll just circle it over here, where we have an elevation in the number of protons. This could be due to loss of function in the kidneys or some other metabolic challenge. You could have consumed a lot of acid, or even a lot of activity can generate a lot of acidity. So these types of things will, your lungs will want to compensate for the production of carbon dioxide that arises as you have an elevation of protons. So scooting back up to this here, if you have more protons, because your kidneys aren't able to pee them off, if you will, then what's going to happen is it's going to push the equation in this direction, and you're going to have more CO2 produced, and that's going to be breathed off. So that helps to cover the points that we have in this slide, and for our for what we talked about in Monday.